Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Ready to rock, Mr. Balhuis.
Hang
I
up.
called you that in a while.
I know.
But, you know, I tried calling you, and Siri, whenever I said call Mr. or not Mr. I'll have you in my phone as Mr. Bullheis.
I hope you still have me as Mr. Bullheis in your phone.
That would be very funny. No, a couple decades on, I've changed it to Chris Bullheis. But I said call Chris Bullheis, and you know, it goes to somebody else in my phone who has a name that starts with a B but is not Bullheis. And I'm like, oh crap, no, and that's not what I meant to call.
You actually have to say it Bullhuis, don't you?
Yeah, I actually do have to say it. Call Chris Balhuis, and then every time Siri gets it right. So,
okay,
I haven't called you that in a while. It makes me feel good inside. It always gives me a little chuckle.
Well, you know what makes me feel good, Jesse, is talking about the Grand Tetons. That's what makes me feel good.
Yes. This is home away from home from you. This is for you, and actually the Bullheis clan. You and your wife and kids, you guys have gone here many, many times, and on your own and with students, teaching students. So this is definitely, you know, your second home, I would say, in a way.
Yeah, I feel like my kids cut their teeth, you know, in the Tetons in terms of their mountaineering and all that, climbing and stuff. They've done a lot of it in the Tetons. Yeah.
So cool. I mean, what a place to do it. So this is, just to set the stage here, this is a video. We're going to show some images here as we work through the geology of the Grand Tetons. These images plus a lot more content, plus like 9 chapters, really visual podcast episodes, are on our app, Camp Geo mobile app. You can go to the first link in your show notes. This is the intro, though. This is, Chris, I love this setup you have. This is, we're going to go in a hot air balloon ride, and we're going to float above this region, and we're going to have a fast forward button through geological time, and we're just going to be able to see these major events that helped form the Grand Tetons that we see today. And this first image here that we're looking at is just an overview. There's time stamps on here. There's events that this GIF is working through, and this is kind of broadly what we're going to cover in this episode. But this is a high-level overview, 30,000 foot view from a hot air balloon. We have the fast forward button. Chris Bullheis is our tour guide. Where do we start with the Tetons?
Well, we got to start with the first page of the book, right? Those are the oldest rocks that we get to see in the Tetons. You know, all the granites and granite gneisses when you're standing in the valley of Jackson Hole Valley, and you look at the core of the mountains. That's where the story really starts, you know, with this really old ancient mountain building event. So we got to go back, you know, 2.7-ish billion years to start telling the story of these rocks. So it's at the bottom of this first image that we're looking at there, that first thing, that what I always call the Precambrian. You like to break up your Precambrian eras in terms of, you know, Proterozoic.
We got to get a little doctor and professor and pretentious about it. You know, these are old rocks. This is my home. This is my like scientific home. Old rocks, old, super deformed stuff. What did continents look like 2.7 billion years ago, 2.5 billion years ago? I mean, the Tetons has some amazing exposure, and there's a bunch of really cool science that's come out of the rocks that are exposed in the Grand Tetons. And I just want to clarify 2 things first, Chris. This image, time, as is often the case in geology, time is not linear here. We start at 2.7 billion years, then we skip ahead to 2.5, then we skip ahead to 750 million years ago. Like, this is not a linear scale with time. As is often the case in geology, we have a lot more information from the recent past, so we know a lot more about that, and this kind of shows that, I think, pretty well.
It's grossly out of scale, right? It's like any image that you might have seen about the scale of the solar system. This is that in terms of the geology of the Tetons.
So, Chris, can I ask? I want to quick question here. Like, if you're tour guiding through the Tetons today, you take students, you're driving the bus, you know, you're going from Jackson, and I forget where the campground is, but you're driving north to.
We usually try to stay at Grovant. Yeah.
Grovant, okay.
Yes.
So you're driving north, and the Tetons on your left side, and you're driving along them for a long ways. If you're just standing there, you have that picturesque view of the Tetons, you're in the valley looking to the west. How much of what you see is this old rock? Like, from the south to the north, if you look left and right, how much is this like really old deformed gneisses and granites?
Almost all of it.
Viewpoint.
Okay. Almost all of it. All of the high peaks are this really, really old stuff. And there's a reason why the high peaks are they're the ones that stand up to erosion the best. And so almost everything you see from that perspective from the valley floor is what we're talking about here. And if you look at image 2 then, Jesse, let's go ahead and bring that up.
Yeah, let's move forward. This is a great one. You sent me this summer, actually. You texted this to me from your trip. You were out there on the summer science trip leading all the high school students, and these beautiful garnet eyes. I mean, these are really cool.
And this is this is the old stuff. It's the Precambrian 2.7 billion year old stuff. Jesse, let's dive in then to let's start telling the story. How did this all begin? How did the Tetons begin? But like we said, we've got to go back 2.7 billion years ago. That's a really long time, but we're still missing. The Earth is 4.5 plus billion years old. We're not going to talk about those first 2 billion years.
Yeah.
There are no rocks that exist that go further back than what we're looking at here in image number 2. So how did this happen, Jesse? Old rocks is your thing. That's what you do, most of your research on. So go ahead and start telling the story. What are we looking at, and how did it get to look like this?
So this rock, Chris, is a great kind of example of what these things typically look like. Sometimes they're more deformed like this. They're more tortured. They look more like toothpaste than this rock does. But this, you can still see it's deformed. You can kind of see, if you get your eye tuned into it, you can see this kind of bottom left to top right, kind of what we call foliation or fabric in the rock. Things are kind of oriented that way, bottom left to kind of top right. And you can see here, we've got these beautiful little garnet eyes, which are these little feldspars that are growing around garnet. It's a representation of a reaction that happens. These are metamorphic rocks. So this was a sediment that was buried down deep, 20 miles deep or something like that, when two plates or microplates collided together and metamorphosed these things. And they heated up so much that they started to melt. And a lot of the rocks that you'll see in the Tetons, that beautiful view and the plains looking towards the Tetons, a lot of the rocks you'll see there are granite that formed around 2.5 billion years ago that also represented kind of this metamorphism, melting, kind of really continent stabilization. This was the continents, the what were smaller continents. These things were stabilizing for the first time. And, that history is locked in these rocks. It's a really beautiful, complicated story. And if you're interested, we have podcast episodes that kind of dive into that deeper history. But these are really old rocks still, These are really old, really tortured. We have to see through many events to get at that original story, that 2.5 billion year old story.
Right. And real quick about this image too, the garnet eyes. Garnets are super important in understanding the story of the Tetons because, the garnets, they tell us very specific temperatures and pressures to which these rocks were subjected to. And the garnets were also, why do we have these white eyes around these dark garnets? Is the garnets, as they were growing within this rock, they were taking what they needed from the minerals that existed in the parent rock before it got metamorphosed, or as it was getting metamorphosed. So it was just extracting out and kind of bleeding out the elements that it needed, which leaves us then with these, it's fairly common, these eyes around garnet crystals.
Yeah, it's such an interesting process. And garnet, it pains me to say it, but garnet is probably one of the more scientifically ususeful minerals out there.
Yeah.
Because
why does that pain you to say that? Why does that hurt?
Well, there's other ones that I work with more professionally that I like more. Zircon, I have zircon's near and dear to my heart and is in the conversation. I would say it's garnet or zircon as the most scientifically useful minerals out there. But garnet's incredibly powerful, especially for seeing into metamorphism like this. So, if you're metamorphic petrologists, people who study metamorphic rocks love garnet and focus on it a lot because it tells this amazing story that you're talking about, Chris. So that's, I would love to spend more time talking about the old rocks here, but we're going to skip ahead a bunch in this time. So
hold on real quick though, Jesse, a really accessible place to get up close and personal with these kinds of rocks is at a very popular destination called Inspiration Point. It's on the other side of Jenny Lake. You can take a boat across there and a boat back, so it's very accessible for really everyone. So just for those students, if they want to get a look at it.
Chris, that's the one where we got caught in a rainstorm with the students in 2019 when I came out on your trip, right? On the ferry ride back. Yeah. That's great. I mean, it's beautiful, but I was surprised at how how big of waves get whipped up on Jenny Lake pretty quickly with a big, Rocky Mountain thunderstorm comes through. It can get pretty bouncy pretty quick on that lake.
You got it. That's right. So, all right, shall we fast forward now, Jesse? We're going to hit the fast forward button.
Yeah, let's do it.
We're going to go from 2.7 billion years ago to 2.5 billion years ago, which seems like not a lot of time. But we really can't think about it that way. 200 million years is a lot of time. The dinosaurs met their extinction 65 million years ago. This is 3 times that time span that we're talking about.
We just can't forget that geologists, we like to make things simple. So we take 200 million years and we kind of compress it to 0.2 billion years. And so it sounds small, right? 2.7 to 2.5 sounds like nothing, but yeah, it's a massive amount of time, a lot of time, right? This is a huge amount of time. And so what happened there, Chris, again, I kind of alluded to this before, but this is melting. So this rock here that we're looking at, this is a metamorphic rock. We can see the garnets in it. This rock has maybe lost a little bit of melt, meaning it is the residual. Chris, you describe it perfectly. Melting never happens on Earth, but partial melting happens all the time. And so these rocks, not this particular one, but rocks a little bit deeper than this, would have gotten to high enough temperatures, 700, 750 degrees, maybe 800, 850 in some extreme cases, where they would have started to melt. And some amount of the quartz and feldspar and some biotite components would have melted out and formed a granite. And these granites then move up, rise up in the crust, and solidify there. And that's the event that's 2.5 billion years ago. We can see these things, the Mount Moran granite, lots of granites in that time period throughout the Tetons and throughout the western United States. And this is really what stabilized the crust. So taking all that magma and moving it up to the surface, what it does is it kind of stratifies the crust so that it's stable. It's like thermally stable now because all of the uranium, potassium, thorium has gotten moved up to the top, and that just makes a stable continent very well. So that's what happened 2.5 billion years ago, and we can tell that by looking at all the granites. And Chris, where's a good spot to see the granites? I mean, I think the answer is kind of everywhere, but like, where's the best spot?
Yeah, I think you can look around too. If you go to Inspiration Point, you'll see these like toothpaste like metamorphic rocks on the other side of Jenny Lake, and you'll also be able to see really coarse grained granite, this intrusive, big crystals of quartz and feldspar in this stuff. It's very, very light colored. There's not a lot of dark mafic minerals in it at all. But you can, if you look around there, and you should, Inspiration Point is called Inspiration Point for a reason. It's beautiful. You can also see granites there too. So you get both of the super old rocks in both of the super old rocks in the Grand Tetons, the metamorphic rocks, the gneisses with all the garnets in it, and the granites that you just talked about, the 2.5 billion year old granite, you can see them there as well.
They're just, it's really an obvious relationship when you see it. I mean, you can see, this rock's deformed, like in this image here that we're showing, and then there's a granite that's not deformed, lots of coarse grains, much lighter colored rock. That's the end of the really old story, 2.5 billion years. Once that happened, the continent's stable and not much happens for quite a long time. And we're going to be in our hot air balloon and we're going to hit fast forward, but we're going to smash the fast forward button and go 10 times 20x, 3,000 million x speed to get ahead right here a little bit really fast.
And a lot's going to happen, right? During that time, it'd be really cool to see. But in terms of the story, we do have to zip right through this. And we're going to go to about 775 million years ago. We're still in the Precambrian, right? I mean, the Precambrian didn't end until, the middle 500 million years ago-ish time range. So we're still in it. But we zipped through a lot of time here. So Jesse, 775.
Let me just touch on this. Why? Why do we fast forward? As you said, there's stuff happening. There's stuff happening on Earth at that time. Why do we skip ahead so fast for this huge interval?
Because there's just a lot of weathering and erosion going on. You had these mountain building events. We started with this shallow sea. Subduction was taking place. Really, really deeply rooted rocks were forming. But there was a lot on top of this. This was a mountain building orogenic event. And then what always follows that? When that event ends, then you have weathering and erosion is the story to be told after that. And you're going to have isostic adjustment going on where the mountains will uplift and then more weathering happens and more uplift will take place and so on. But that's the story for the better part of 2 billion years.
Exactly, in this particular region. And I mean, we don't have a rock record from the Tetons of, a lot of the stuff that's happening. What was going on was these microcontinents were 2.5 billion year old continental plates were smashing into each other 1.9 billion years ago, but we don't have that record in the Tetons. We can piece that together where we step back and look at broader North America, but we don't have that story in the Tetons. So we're going to kind of focus on what rocks do we have from the Tetons and what can we say from that? And we don't have anything from this interval. So the next major rock event that's recorded, and is a really beautiful one, Chris. I love this story. It's one everybody can see. You don't need to get out of your car to see this and understand the power of Earth processes, really. What's the next thing at 775 million years ago?
We have these diabase intrusions that are taking place. And if you look at this image number 3 here, great example of it. It's a GIF showing the diabase dike. This is the famous one that cuts right through Mount Moran. That's about 100 feet wide, what we're looking at here. So, and it goes all the way through the back side of the Tetons. This is the most famous of the diabase intrusions. It's not the only one. The Tetons have all kinds of these that are cutting through these high peaked mountains. My favorite one actually it's my favorite, I think, because it's harder to get to and harder to see, but that's going to be cutting right through the middle Teton. It's much narrower, so we had 775 million years ago,
Chris,
Jesse,
hold on real quick. Is there a hike that people can go on to see that you can get access to it, or is it just get in the backcountry behind the middle Teton?
So the Lupin Meadows trailhead will take you up to places like Delta Lake or Surprise Lake and Amphitheater Lake, which are all places I absolutely love. But there is a junction where you cut off the other direction and go towards what's called Garnet Canyon. And it's called Garnet Canyon because it's full of these garnet eyes that we showed earlier. If you hike up to Garnet Canyon, this is where most of the climbers are headed that are going to do the Grand, or they're going to do the Middle or the South and various other peaks. But you can get into Garnet Canyon and get a great view of the Middle Teton. You don't have to go climbing. You can just get there. It's absolutely a beautiful place. It's hard to get to, though, from the standpoint if you got to work hard. It's it's not an easy hike.
Yeah. Yeah, sure.
Yeah.
As you
so
can
I
probably
love
tell
that.
by looking at the Tetons. Yeah.
Jesse, what was going on? First of all of these intrusions in the Tetons, they're running this kind of east-west direction. What does that mean to us as geoscientists?
So we get into this. It's a really cool, a little bit more complicated story. So we don't have the time right now to get into it. But if you, in our Camp Geo content on our app, we have a whole chapter on this. And this is really, people have proposed that these dikes, represents kind of stretching of the crust, and stretching and magma intruding. And so you have to kind of ask, why is the crust stretching? Where's the magma coming from? And those two things, people can go around and date these dikes. They're hard to date actually really accurately, but people have done it before. And if you grab a sample of that, look at some of the minerals in it, say, when did this dike actually form? This can be related and has been related to what's called the gun barrel event, which is a whole bunch of dikes around Western North America that all are kind of the same age, same general composition. And they don't all go in the same direction, though, but they all kind of point to an area just offshore of the Pacific, what is now the Pacific Northwest. And so one of the ideas is that there was a big plume event out there, that the plume kind of punched up through the crust and stretched the crust all around it, and then you get these radial cracking events that get filled with magma from that plume event, all kind of roughly in this time interval, 780 to 750, that kind of ballpark area. And so that's one of the theories for the formation of a lot of these dikes that are going through there. But they're beautiful. They just cut straight across. You can kind of see contact metamorphism along it and along the edges of the dikes, because they bring in so much heat to the crust that they metamorphose the rock right next door. So anyway,
and the idea is that there was some extension going on, and that extension caused the cracking, right. And the cracking then filled in with this mafic diabase rock. Jesse, one other thing real quick about this is if you take the exposed portion, just the exposed portion of the dike cutting through Mount Moran, it's enough material. If you melted all of it, it would be enough material to fill in Jenny Lake 3 times over. That's
Wow, that's a
Jenny
great
Lake is a
visual.
big lake. That's amazing.
That is a great visual. And a lot of people will see Jenny Lake. If you're going to the Tetons, you'll see Jenny Lake. That's a great visual. So if you just take what we've mapped, that volume, it would fill up the lake 3 times over. That's very cool.
Right. Yeah,
It's a huge amount.
absolutely.
And this stuff is going thousands of kilometers, right? This is, not this one dike, but many of them you can trace for a long, long ways, and then you pick up another dike, and this crust was stretching over a huge region. And remember, this was pretty deep at the time. This was not at the surface. This was down at depth that this stuff was happening. So totally cool event and really cool geological story. Again, we're in the 780, 750 million year range.
Right. If this was at the surface, then we wouldn't refer to it as diabase. It would be just basalt then. So the only difference between them is where they happen. They're chemically the same material, but that just real quick, that's why we call it diabase. So Jesse, we got to fast forward again. Okay. We got to go hit the button and go about 250 million years closer to present day now. So we're looking at just over 500 million years ago, like 510-ish million years ago. And at this time,
Hey, Chris, let me interrupt real quick because this is represented before I move forward in the slide deck here. This is represented. We can see this rock. You can't really see it in this image, but right up in here where there's snow at the top of Mount Moran, there'll be some rocks up there that represent this event and kind of show another cool geological relationship that is a sedimentary rock at the top.
So when you're there looking at this beautiful scenery in the valley, get your binoculars out and look at the top of Mount Moran, and you will see this kind of blonde-colored, tan-colored sandstone up there. It's about 30 to 40 feet thick, and that material was deposited in the next event that we're going to talk about right now, which is this very shallow sea began to invade the Teton region. So this is hard to imagine, right, Jesse, that they don't look like they look now. We're talking about the area being relatively flat. These deep-seated rocks, these granites and gneisses and the diabase dikes, all this Precambrian stuff was exposed now at the surface. These were deeply rooted rocks that got brought gradually to the surface.
Can I skip ahead a couple of slides here, Chris, and just show the interior seaway? I know this is not the seaway we're talking about it, but it just kind of gives us the topography of what this place might have looked like. It's not exactly this. This is a younger seaway event, but kind of the same vibe. We've got mountains. These things are getting eroded down. The sea is invading, whether sea level's rising or the region is subsiding, the land is subsiding. Both of those can give you relative sea level rise. So it's getting flooded, what is the answer? And if we go back to Mount Moran here, you have to ask yourself, wait a minute, this is metamorphic rock. Mount Moran is metamorphic and igneous rock. There's an igneous rock cutting across it, and then we have sediment on top. So geological intuition, the most fundamental geological intuition tells us that peak of that mountain used to be below sea level because there's sediment sitting on top of it. And then it got somehow thrust up between 510 million years ago and now, right? So that's how this works.
We know that for sure because the sedimentary rocks are unaltered. You go from these tortured rocks, these metamorphic, deep-seated, lots of heat, lots of pressure, to all of a sudden sedimentary that has no signs of being cooked at all. So that's in geology, we call that a non-conformity. There's a lot of missing time between the formation of those old rocks and then the much younger sedimentary rocks that we're going to talk about here. So on top of Mount Moran, you're looking at the Flathead sandstone, but there's a record of all kinds of sandstones, shales, limestones, and then tons of fossils as life began to change quite, kind of rapidly in this area. These fossils were preserved in these rocks. And one of the best places to see these sedimentary rocks, Jesse, is on the back side of the Tetons, like on the Idaho side, coming into the very famous Alaska Basin. It's a destination for many, many, many hikers. And that's where you get to see this really almost continuous record of sedimentary deposition. It's a lot. It's unbelievable.
Yeah,
So,
it's huge. I mean,
yeah.
these sediments, so we got trilobites here, we've got ichthyosaurs. We can look at the fossils in this huge sedimentary package, and we can see how life is changing, how life is evolving through this time interval, because this is a long period of not continuous deposition, but kind of on again, off again deposition. And we talk about this in our Grand Canyon visual podcast series. It's well represented, this sedimentary story, all over the western United States. We just have a little snippet of it at the top of Mount Moran, and then more on the backside. And as you're standing there, as you're looking at the Grand Tetons, you should think about, and this is a leading thought, you should think about, where are all the sediments in the Tetons? As you're standing there in the valley and you're looking up, you see the little bit of flathead sandstone at the top of Mount Moran. There's a whole bunch on the backside. Where is it? Where's the rest of it? Right? Think about that, and that gives us a clue as to how the Teton Mountains actually form. But
can we talk about that right now or not? Like, where they are, or do you want to just wait? Yeah,
on that part of the story? Let's skip ahead here a minute. Because
right now they're like 6,000 feet above the valley floor. That's the top of Mount Moran. So that same sandstone is beneath the valley. It's beneath Jackson Hole, and you have to go down about 24,000 feet to reach that flathead sandstone. So Jesse, you're talking about an offset of 30,000 feet, and we'll talk about the cause of that offset later on in the story. It's one of the more recent stories that is told in the Tetons, but 30,000 feet, that's a lot.
Yeah. It's massive. So, Chris, let's just tidy up this sediment deposition thing. This story is very detailed. We can focus on it a lot, but we don't.
And we do.
Because, again, we don't have a massive amount of these sediments in the Tetons that you're looking at. If you go to the Grand Canyon, if you go to Zion or Bryce or Canyonlands, anywhere else in the western United States, you'll see snippets or huge pieces of this story of this interior sea coming and going, and different rocks being deposited across this western United States area. So that's the end of that story. And then what happens next, Chris, in our hot air balloon? Where are we at in time, and what's happening if we look out over the wicker basket?
We had seas coming and going, the shallow seas. They would transgress, they would regress, and this went on for a really, really long time. And there were many seas, and they have names, and you showed the GIF there. We've got the GIF of the Western Interior Sea, which is the most recent one. So what drained this sea for the last time? It went away, and then it was never going to come back. At least it hasn't yet, right? And so
what time period are we at, Chris? First of all, what's the timestamp? What are we looking at?
We're going to fast forward to about 160 million years ago, where mountain building further to the west started happening. And as that compression happened, then that thickened the crust, which drained the sea, and eventually mountains began to form in the Teton region. Not that they look like they do now. So 160 million years ago, and this is ish, that has a name. It's kind of a famous mountain building event, and it's called the severe orogeny. And if you look at this next GIF, this is a schematic that we made showing the severe orogeny and then the later on Laramide orogeny. There's a little bit of overlap with these two very famous mountain building events in the western U.S. So basically we had an oceanic plate subducting beneath North America.
Yeah. So this image here, and we're going to skip ahead a little bit. So you said severe 160, then, there's a little bit more sediment deposition going on. And then around 80 million years, this is when the Laramide starts. And this is when the sea gets drained and does not come back for the final time. So 80 million years ago, the Laramide kind of kicks off. And this image, I just want to put a massive caveat on this image. This is the traditionalist view. This is the textbook view. This is the paradigm that has existed for the last 30 years of what caused the Laramide orogeny, which is called the flat slab model. And the way to think about this, and the way to
it's very
think
controversial.
About this, traditional model, this is the traditional model, is that you have this subduction zone happening. So in the blue in this image is an oceanic plate that's subducting beneath. For some reason in the traditional model, that slab flattens out and starts to slide underneath the continent. And as it slides underneath the continent, it kind of, in a very simplistic way, just pushes up the continental crust. And that's what we're kind of showing in the last couple frames of this image. Flat slab model creates this really, as you described, Chris, beautifully muscular mountain range, this thick skin deformation, meaning thick skin, as opposed to the severe, which was more of a thin skin process. Thick skin, meaning you're getting these basement rocks, these old gneisses and old granites are getting thrust up to the surface. You're getting really deep faulting going on here. And so that's the traditional view of the Laramide. If you're watching this on YouTube, we've got an interview coming up with Basil Tikoff where he presents a alternative view for how the Rocky Mountains formed and how the Laramide orogeny formed, an alternative tectonic view, which is very, very different from this. So I would say, Chris, what the Laramide orogeny represents tectonically is up for debate. And there's kind of three current models. One would be this old flat slab model, the traditional flat slab model. Basil has a hit and run model, and there's another model out there. So this is very much an interval of, or this is very much a topic of ongoing scientific debate, newly reinvigorated scientific debate, which I find really exciting. Like the Rocky Mountains, we're revisiting how the Rocky Mountains formed. Such a cool topic.
Absolutely.
Anyway,
but what we do know is that we were getting thick skinned mountains, these young muscular mountains from deep, deep rooted. We're getting shoved up, and it was however it happened, a very spectacular mountain building event was taking place.
That's exactly right. We're getting all this beautiful topography that's going on here. And then, Chris, is it fair to go forward to our schematic of the Tetons? We're going to zoom in on the Teton region now here. And what's happening here? How do we get sandstone way up high and it's way down beneath our feet? That's kind of the question, right?
Right. So we have to fast forward. So the Laramide, however it happened, ended, it didn't all end at the same time in the same place, but about 50 million years ago, it had ended. And so we're going to fast forward to about 10 million years ago. So we're going to zip through about 40 million years of time here. And this is the event that is going to bring us to like where the Tetons look a lot more like they do today. It started about 10 million years ago. And this is the Teton Fault that we're looking at in this kind of schematic here. Basically, it's a massive normal fault that has, like we said earlier, 30,000 feet of displacement currently. So if you think about these sedimentary rocks as a blanket across the region.
We just need to say that word again. 30,000 feet of displacement. That means Mount Moran sandstone 6,000 feet above your head if you're standing in the valley. Flathead sandstone on the top of Mount Moran 6,000 feet above your head. Flathead sandstone beneath your feet 24,000 feet beneath your feet in that valley floor. That's 30,000 foot of movement. That's what that means. The rock unit has been broken and the two pieces separated by 30,000 feet of vertical movement. That's amazing.
And what we have going on, really, what brought this about was maybe counterintuitive to a lot of people. We think of mountains as being compression events all the time, tectonic collisions that are taking place. This actually was brought about by expansion. This area was being pulled apart, and that creates then what's called a normal fault. And that is our beloved Teton Fault here that we're looking at. And so basically, it's pull it apart, and then you would have these episodic, very violent earthquakes that would cause the valley, Jackson Hole, to sink and the Tetons rise in these violent. So these are mountains that are made more of seismic disaster than compression and the related volcanism that you would get with that kind of.
Yeah. And this GIF, Chris, is just this is a very simplistic GIF, very much simplified, but shows the full story. So we start out here with deformation and distillation of the crust, then we have sediment deposition, and then we start to have this faulting event. I mean, we kind of skip over the Laramide in this GIF, but we start to have this extension, this tension, pulling apart, and you get this saloon door. You describe it as saloon doors, kind of swinging. One end swings down and one end swings up. We get this separation, and it gets complicated here. Like the root cause of this deformation certainly probably related to basin and range extension in some way. Perhaps there's some influence of what we'll talk about in a little bit, the Yellowstone plume event that's kind of scraping across this region as well. It's unclear like what's the main driver of all of this. There's certainly a bunch of factors at play to make this Teton fault door system like swing open so wildly.
So, Jesse, there is a place that you can go and see the most recent movement along the Teton Fault. I just took a group of students there this summer. It's called the Cathedral Group Turnout, and this is on the Jenny Lake Scenic Loop Drive.
Yeah.
And you can, if you look across the vista, and there's a one of those national park, what do you call them? Those those placards that it kind of explain what you're looking at right in front of you.
Scientific. Yeah, signage that tells you what's going on. Yeah.
So you'll be able to look at that sign and then in the distance see movement along the Teton Fault. And this was movement that took place, about 10,000 years ago, where it cuts across the glacial sediment that was deposited at the end of the last ice age. So that puts a good timestamp on that movement for us. And you can just easily see the scarp. Now, this summer, I took a group there, and we get to the turnout, and I'm so excited because I love like being able to see the geology that you've talked about and are still talking about. Is just really, really cool. It's the best textbook in the world. Get off the bus, and we really couldn't see 10 feet. We were socked in with fog, so it was disappointing. I'm like, well, this is what you should be seeing,
Yeah, you start drawing on the side of the bus. This is what you'd see off there at the distance.
That's exactly
if you could
what I
right?
did too.
Yeah.
Get out my dry erase markers and start marking up the windows. Yep.
Yeah, you got to, right? I mean, you're right. It's such a beautiful, some of these textbook examples, examples that are in the textbooks because of it's such a spectacular preservation of geological events. Chris, let's keep this going here, and let's move ahead. Let's fast forward a little bit more. So you said 10 million years kind of starts the Teton Fault. Around 5 million years, the Yellowstone hotspot, and we have a visual podcast series on Yellowstone National Park and all the interesting geology there. As it relates to Tetons, about 5 million years ago, those eruptions started in this region. And so that certainly has some effect on the Tetons.
Yeah, absolutely it does.
It's sort of open science of how much, and what factors were driven by Yellowstone versus some people would say that the Teton Fault actually cuts through Yellowstone, and it's actually an older process, and Yellowstone maybe didn't drive the Teton Fault as much. It's kind of a chicken or the egg discussion at the moment. That's very much, I think, unsettled science.
I guess, but I will say this, that the uplift definitely accelerated with the proximity of the Yellowstone hotspot. So we say that the Tetons are, the Teton Fault began 10 million years ago, but a lot of the uplift happened more recently than that.
So you're saying that you would think it would be driven by Yellowstone.
I'm just saying there's a correlation. I don't know if that's cause and effect thing or not, but I think that's where the thought comes from, I guess we'll say.
So you get this uplift, you get Yellowstone kind of traversing the area and affecting the region. I mean, certainly. But that's, I think, less impactful, Chris, than the glacial events that will happen here. And the glacial events are in part driven by Yellowstone as well, and the topography and the sort of the ice cap that sat on top of Yellowstone. So there's a lot of feedbacks between these two. But what did ice do here? If we kind of
I
skip
have
ahead.
One thought though. Hold on. I want to go back a second to the Yellowstone thing. The track of the hotspot. I'm just so grateful that it went where it did. Because if the track had been a little bit further south, it just would have buzzed right on through the core of the Tetons, and it would have destroyed my beloved mountains. And I'm grateful to Yellowstone for staying north. Okay, so
stay north. That's exactly right. Don't destroy the Tetons.
Ice. I love this GIF that we've got up here. That's actually a picture that I took that then you GIFified. This is a picture of Schoolroom Glacier. And it's
why is it called schoolroom, Chris? Well, it's called schoolroom because it's a textbook example of alpine glaciation and some of the features that are driven by alpine glaciation.
Absolutely. You can see that there's a cut at the end of that moraine there that dams in that lake, and you can walk right through that cut. So I've actually, dipped
Walk
myself
down there.
and cleansed, a little bit down in that lake. It's really super cold, but it's awesome.
I mean, I would imagine, yeah.
I mean, I don't know, Jesse. What did glaciers do in the Tetons? They made the Tetons beautiful. Glaciers, they make angularity when they erode. This is what gives us the horns and the arêtes and the cirques and the tarns that I just love to. Whenever I see a tarn, I got to go swim in it. It's just a thing.
It's a requirement for you.
Yeah. And so they sculpted the Tetons to make these spectacular cathedral-looking peaks. And it ended about, 14-ish, give or take, 1,000 years ago for the last time. This began about 200,000 years ago, the work of ice here.
The question would be, why is there so much ice sculpting here? And the answer is in part due to Yellowstone. There's this ice cap that would sit up in Yellowstone just because of topography and precipitation that we talk about that a little bit more in some of the audiobook chapters. But you get an ice cap up there that then sends a lot of ice and downhill, down towards the Tetons. But you also have these alpine glaciers, and you get a lot of precipitation as it's cooling. So we get the Bull Lake glacial event. We get the Pinedale glacial event, which you mentioned, some of the Marauder minimum, some of these younger ones, but you get ice accumulating, and this GIF here is showing we're kind of looking from the glacial perspective. So there would have, and there is a little bit of a glacier here still, but it would have been bigger.
It's a sad little remnant. Yeah.
It's a sad remnant. It would have been flowing downhill, bringing sediment, and it was melting where this moraine is, where this hill is here. That's all sediment that was carried down by the glacier. And then as the glacier melted, it filled in that area with a lake, and then the lake ripped through this dam of the moraine and created a little river channel, and we still have the lake there, moraine dammed lake. And so this is just one little example of, I would classify this as little for
it is little,
events,
but Jesse, actually, this right here, there was what's called the Little Ice Age that happened between 1400 and 1850 AD, where it was tied to the sunspot cycle. That there was a period of time where the sun had unusual low sunspot activity, and that affected climate in North America and other parts of Europe too, where it caused cooling, and we had a little ice age that was going on. And so the glaciers returned very briefly and formed a lot of features that we see still in the Tetons today, which I think is really, really cool.
It's very cool. And I think, Chris, are we kind of ready to wrap up the geology of the overview of the geology of the Tetons here? Because I think that point that you just ended on really drives home, for me, the beauty of the Tetons. We've talked about Yellowstone, which is amazing in many ways, but it's kind of a snapshot in time. I mean, most of the interesting stuff happening in Yellowstone has happened recently in the last 5 million years. The Grand Canyon is amazing, but it's a sediment story of the last, 500 million years. The Tetons are exceptional because you get the full gamut of geology, from really old rocks and complicated garnet petrology stories talking about ancient mountain building to crustal stabilization, and you get the sediment stories, and you get young glacial stories too. Like, you kind of can teach the intro to geology the full range of processes in the Tetons. And we haven't even talked about the Snake River Plain, and you can talk about, all sorts of interesting things about river morphology. It's just an amazing, I can see why you love it and why you love to teach students there, because you get to teach everything. It's amazing.
I mean, we're looking at, we started with 2.7 billion year old gneiss, and we're looking at now a glacial deposit that is under 200 years old. You're right. It does. It spans the whole gamut. But the thing, you have to travel. You have to, not all of this is easily accessible in the Tetons. So if you're able and you plan it out well, you can see it all, though.
That's right. And like many of the Western United States national parks, the signage and the turnoffs are very well placed to see very important geological events. I mean, the Tetons is a geology park. Well, geology runs everything really in the world, but
it does.
But this in particular in the Tetons, it's just hits you, it stands up and slaps you in the face. You got to understand geology because it explains everything that you're seeing. It's just an amazing park, just an amazing park. So, what do you think, Chris? Is that, it's hard to say we did it justice because it's an intro, an overview, but that was a pretty good hot air balloon ride, I'd say.
Yeah, I agree. Yeah, I think that's a wrap.
If you have thoughts, questions that you want us to address, put them in the comments section. Again, you can get a lot more information. We have 10 chapters in our visual podcast series on the Grand Tetons National Park. It's the first link in your show notes, our Camp Geo mobile app. Go there. We also go to our podcast on any podcast feed. You can follow the Planet Geo podcast on Spotify, Apple Podcasts, wherever you get your podcast. Follow us there. Leave a like and subscribe if you will. Cheers.